Hi folks. The purpose of this video is to go over the answers to Microtask Tool 1 so that you can check your work. If you haven't already done Tool 1, pause the video and do it now. Should take you like 15 minutes. And once you're done, come back and let's talk about your answers. I'm assuming that if you're watching this now, that means you're done. So, okay, let's talk. I want you to check your work because I want you to get the right answers and understand why the right answers are right before you do the practice assignment for Tool 1. So, the first questions are here on page 2. What are the number of significant digits for each of these numbers? Okay, so for the first one here, pretty easy, right? 132 has 3 significant digits, right? Remember that significant digits are all about reporting the level of honest accuracy for a given number. Right? So if you're saying, all right, if you're saying I made a measurement and my measurement is 132, could it be, is it exactly 132? Or is that just the closest thing you've got to a right answer? Well, you don't know, right? Because if you made a measurement and you're saying, okay, I measured 132, well, could it be 131.9? Well, maybe. Could it be 132.1? Well, maybe, right? But you don't know that level of accuracy. You don't know what the fourth digit is, right? All you know is that your measurement is limited to an accuracy of 3 digits, 3 significant digits. What's the fourth digit? You don't know. Your measurement wasn't that precise. So you're going to say, okay, I have an answer to 3 digits. Okay. What about 10? Okay, you might think well, 10 is 2 digits, right? Well, it is 2 digits, yes, but are they both significant? Is it exactly 10? Or could it be 9? Could it be 11? Or could it be 10.1? Could it be 9.9? The tricky thing is where there's a 0, right? Sometimes a 0 is significant, sometimes it's not. And like I said in the lecture, the way to know whether a 0 is significant is to turn the number into scientific notation, right? Turn this into scientific notation. And what do you get? You'd get 1 times 10 to the first power, right? 1 times 10 to the first power. Well, the number of digits out front here, that's the number of significant digits. So if you convert this into scientific notation and the 0 disappeared, then it wasn't significant. So since this only had 1 digit, then 10 only has 1 significant digit. The 0 wasn't significant. And sort of like I was hinting at a second ago, what does that mean to say it only has 1 significant digit? What it means is that you measured 10, but maybe it's 11. Maybe it's 9. Maybe it's 9.5. Maybe it's 10.5, right? The first digit is the one you're sure about. It's a 1. What's the second one, though? You think it's 10, but maybe it's 11. Maybe it's 12. But you know for sure it's not 20. You know that first digit is a 1. Okay? Converting into scientific notation is the way to be sure. Okay? Okay. How about this one? 5.40. And again, oof, is that 0 significant or not? Well, if you converted this into scientific notation to check and see whether the 0 was significant, you wouldn't actually change the number. Because remember, in scientific notation, right? In scientific notation, you always have 1 digit to the left of the decimal. It's always going to be number dot number times 10 to the something, right? And so since you already have 5.40, since you already have one digit to the left of the decimal, this is the number in scientific notation. And you've got 1, 2, 3 significant digits. Right? If that doesn't quite make sense, let's look at the next one here, right? 5.4. How many digits is that? Well, that's 2. Right? 5.4. There you go. 2 digits. So what is the difference between these two numbers? 5.40 and 5.4. Yeah, they have the same value, right? 5.40, 5.4, they have the same value, but you're reporting your answer to different levels of accuracy. What you're saying here is, okay, I made this measurement and my answer is 5.4. Could it be, what's the next digit? I don't know. I only know the first two, right? Could be 5.41. Could be 5.39. I don't know. I only know the first two. It's 5.4. I got to round to 2 digits. 2 significant digits. If you say 5.40, what you are implicitly saying is, I know what the third digit is. I've measured the third digit. It is 5.40. What's the next digit? That's where I don't know anymore. It could be 5.401. Could be 5.402. I don't know. But I've made the measurement. This is a better measurement. I know what the first 3 digits are. It's 5.40. 3 digits. Whereas here, you only know the first 2. Could the third one be a 0? Could be. I don't know. Could it be a 1? Could it be a 2? Maybe. I don't know. I only know the first 2. See the difference? Okay. What about this one here? 0.101. Is that 0 significant? Let's convert this into scientific notation and find out, right? Turn this into scientific notation and you've got 1.01 times 10 to the, negative 1, right? Okay. 1.01 times 10 to the negative 1. If there's 3 digits in the number out front, I keep saying that. The number out front here technically is what's called the mantissa. It's not important. That's just jargon. So you don't need to memorize that. I'm just, sounds kind of hokey if I just say the number out front. But yeah, so if there's 3 digits in the mantissa, then they must all 3 of them be significant. If this 0 wasn't significant, it would have disappeared. So 3 digits here. How about this one? Right? Let's turn this into scientific notation to check. In scientific notation, this will be 1.1 times 10 to the negative 2. And there you go. If there's only 2 digits out front, if there's only 2 digits in the mantissa, then it must only be 2 significant digits. Okay? All right, let's get a little more practice here on page 3. All right. Write each of these to 3 significant digits. Okay. Use scientific notation if you wish. You're probably going to want to, but maybe you don't have to. All right. This first one here. 2,897,768.5. Whew. All right. Well, this is a big number. I bet scientific notation is going to help us out. So let's convert this into scientific notation, in which case it becomes 2.89776.8. You know what? Yeah, I need more room. I didn't give myself enough room. This is why we work in pencil. Okay. I'll do it up here. Okay. 2.8977685 times 10 to the what? 1, 2, 3, 4, 5, 6. I moved the decimal place 6 places to the left, so it becomes 10 to the 6. Okay. I haven't rounded yet. I've just turned this number into scientific notation, and I've got too many digits, right? So now I need to round to 3. So now it's easy, right? Round to 3 digits. 1, 2, 3. The rest drop out. Right? Except, so it should be 2.89, but then the next digit is a 7. So you got to round up, right? So then it becomes, instead of 2.89, I round up and it becomes 2.90 times 10 to the 6. And again, that 0 is significant because it was a 9 and I rounded it up, right? So I'm telling you, if you report this, you're saying, I've measured it to 3 significant digits. I'm telling you the first digit's a 2, the second one's a 9, third digit's a 0. I've measured the third digit as a 0. There you go. All right. This one's easier because we've already got this in scientific notation. So round this to 3 significant digits. Okay, 1, 2, 3, gone. Right? Except it's a 5. So you round up. So then rounding that third digit up, the number to 3 significant digits should be 4.15 times 10 to the 3. Notice what I did in both of these cases, right? You gotta pay attention to the power of 10, right? The power of 10, here and here, that's the number that tells you how big the value is, right? When you're rounding to the right number of significant digits, you don't want to change the value. You wouldn't just write down 4.15 because 4.15 is 4, right? 10 to the third is 1,000. 4.15 times 10 to the 3 is 4,000, right? If you ignore the power of 10, then you've taken 4,000 and you've just turned it into 4, and you haven't rounded, you've radically changed the value of the number, right? You wouldn't just write down 2.90 because the correct answer is 2.90 million, right? 10 to the 6 is a million. So you got to remember, you got to keep the power of 10, like I said in the video, right? The power of 10 is the most important number because it tells you how big the number is. Everything out here, everything in the mantissa is details, right? And so you're saying, I'm rounding to the right level of detail. I'm rounding to 3 digits, not 4, not 8. So there's your number, there's your value rounded to the right level of accuracy. Okay, how about this one? All right, like we did before, let's turn this into scientific notation to make our lives easier. And in scientific notation, this becomes 3.643 times 10 to the 1, 2, 3. I moved the decimal 3 places to the right, so it's 10 to the negative 3. And then you round to 3 significant digits. 1, 2, 3, that drops away, and that was a 3, so you're going to round down, so it's just 3.64 times 10 to the negative 3. Done. All right. Here, again, you've only got 1 digit to the left of the decimal, so it's basically already in scientific notation, so you just count. 1, 2, 3, the rest drop away, the 6 rounds up, right? The 6 that you're dropping away would round up the next digit, so it's just 5.44. There you go. All right. Let's do this in the opposite direction here, right? Let's take these numbers with 3 significant digits and turn them from scientific notation into standard notation. Okay. So you got 299, so it was 2.99, sorry, not 299, 2.99, and then you're going to move it 5 places to get it back into standard notation. So you'd go 1, 2, 3, 4, 5, and every place that you moved it where there wasn't a digit, you put zeros as a placeholder. So there we go. The answer is 299,000. I'll throw a comma in there to make our lives easier. So the answer is 299,000. And again, those 3 are significant. just like this. Those zeros aren't significant because if we converted it into scientific notation, they would disappear. There you go. All right. How about this? All right, so we've got 2.74. And I'm going to move it 3 places to the left. 1, 2, 3. And where there was nothing, I'm going to put a 0 as a placeholder. And so this then becomes 0.00274. Sure. Okay. How about this? All right, let's see. 1.50 times 10 to the 8. All right, so I'm going to move it 8 places. 1, 2, 3, 4, 5, 6, 7, 8. Okay. And then 1, 2, 3, 4, 5, 6 extra zeros. Isn't this a pain in the butt? Yeah, this is why we don't use standard notation for giant numbers like this. If you got a giant number like 10 to the 8, just leave it in scientific notation. But they want us, well, I want you to put this in standard notation. So what do? You'd put, so 1, 5, and then 1, 2, 3, 4, 5, 6, 7 extra zeros. 1, 2, 3, 4, 5, 6, 7. And then we'll throw in some commas. Okay, it's 150 million. Here's the problem. There's a problem here. And it's not, we didn't do anything wrong. It's just that look at this number. This looks like it only has 2 significant digits, right? That here, the 0 is significant. We've got 3 significant digits. You can't tell this 0 from all these other zeros. They're all just zeros. So if you just looked at this number would look like it only has 2 significant digits, and we've lost a level of significance. We've lost accuracy. Because standard notation doesn't deal with significant zeros as well as scientific notation does. So how do we record this number with 3 significant digits? And the answer is there's kind of no elegant, nice way to do it. You could, I mean, honestly, the simplest, most straightforward way to do it is the clunky way of saying, okay, my answer is 150 million to 3 significant digits. And that's what you would write down. That's what you would, if you made this measurement and you reported it, this is what you would report. 150 million to 3 significant digits. What a mouthful. Or just leave it in scientific notation and make your life easier. Right? So this is the other reason why we don't usually use standard notation for these huge numbers, is that you got to write a whole bunch of zeros and commas for no reason. And also, you might, the number of significant digits might be ambiguous or just outright deceptive. So just stick with scientific notation. Your life will be easier for it. Okay, how about this last one here? 6.40 times 10 to the 1. So 6.40 times 10 to the 1. So I'm going to move the decimal 1 place to the right, 1 place to the right, to convert it back into standard notation. So it becomes 64.0. And notice, not 64, right? Because if I just said 64, I'd be lying to you. I would be saying, oh, my measurement wasn't as good. I only have 2 significant digits. Nah, right? You had 3 significant digits here. Keep them. Don't report a number that's less accurate than the one that you actually measured. Say 64.0. You know what that third digit is. You measured it. You said it's a 0. What's the 4th digit? Well, that one you don't know. But no sense dropping off the 0 when it was significant before. It should stay significant after. Here it's a little clearer than over here, right? Over here, this 0 is significant, but the rest of them aren't, and how do you denote that? That's a mess. Here, if you just said 64.0, then you're reporting all 3 digits, and therefore, if you're reporting all 3 digits, they'd better be significant. Okay. How about the rest of these? Here's where let's break out a spreadsheet. We're going to do some math, and rather than doing it on a calculator, let's break out a spreadsheet and have it do the math for us. All right? Give me a second here, and okay. Make this a little bigger so it's easier for all of us to read, and here we go. Question 3. All right. Here in question 3, we're calculating L. We're calculating L in terms of F and P. So basically, you got to measure F, you got to measure P. You plug them both in there, and that'll calculate the value of L. So how can we do that in a spreadsheet? Well, let's put F in here, and let's put P here. So I'm just gonna label this. I'm gonna label my spreadsheet, and then it'll calculate LS here. What is my value of F? Well, F is 3.839 times 10 to the 26, which in a spreadsheet, it'll use the E notation just like your calculator will. So I'm going to write 3.839 E26. All right? And the calculator will say, okay, 3.839. Well, it rounded to 3 significant digits for some reason. So let's... no sense doing that. So let's see. I'm going to go to Format Cells, and I'm going to say, don't make it 3.83, don't make it 3.84, make it 3.839, just like I entered it. Okay. P is 3.26 E minus 2, right? 3.26 times 10 to the minus 2, same thing. Okay. That it didn't reformat because it was already in 3 significant digits. And now I'm going to use my spreadsheet to calculate L sub S, given the formula that we have here. Okay. So remember what I said in the lecture, right? If you're going to have your spreadsheet do some math for you, you start out with equals. All right? LS equals what? LS equals 9.94 E6, right? 9.94 times 10 to the 6 times pi, right? What is pi? Well, I could type out 3.14159 blah, 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 blah. I could do that. That would be fine. But there's a nice little shortcut programmed into basically every spreadsheet where if you want to enter the value of pi, all you got to do is type pi and then open close parentheses. And that is basically a shortcut. It's where typing pi and then open close parentheses will tell the program, go grab the value of pi, stick it in right there. Where, like, let me show you, I'll just show you here, like, equals pi, open close parentheses, right? If I just put equals pi, it goes and grabs the value of pi and sticks it in right there. Okay, so we've got 9.94 times 10 to the 6 times pi times f. It's kind of cutting it. It's kind of cutting off the text here. Let's see. You know what? I'll make this a little bigger so it's easier for you to read. Okay, there we go. So notice I put in 9.94 times 10 to the 6, and then it just automatically converted it into standard notation. It's the same value, so who cares? All right, so 9.94 E6 times pi times A1. Oops, that's not going to be helpful, right? Because A1 is not where the value of F is. I just wrote F as a label, so that's not good. There we go, right? So I put in B1 so that my program will just take whatever value of f I put into B1 and it'll copy it over right there. So I got 9 times 10 to the 6 times pi times f divided by p squared. What's my value of p? It's whatever's in B2 and then square it. All right. And now there's my answer, 1.328 times 10 to the 37. Well, we got to round this to the right number of significant digits, right? Because remember, the rule of thumb is your answer cannot be more accurate than the least accurate of your measurements. And in this case, we measured f and we measured p to calculate L. Did we round to the right number of significant digits? Well, let's see here, right? How many significant digits does f have? 4. How many significant digits does p have? 3. So if one measurement has 4 significant digits and one has 3, I got to round to 3, right? You have to round your answer to the lowest number of significant digits, because that is the 3 significant digits is all I can justify in my answer. My value of p here is what's limiting the accuracy of my answer. So I'm not going to write down 1.128 times 10 to the 37. I got to round to 3. So I'm going to round to 1.1, right? Can't use the 8. I'm going to round to 1.13. Okay. So there's my answer. 1.13 times 10 to the 37. That's my answer, rounded to the right level of accuracy. Okay. How about number 4? Similar situation. Grab this spreadsheet here. And instead of f and p, I'm calculating r by measuring L and T. So I measure L, I measure T, I calculate RS, and it's a totally different formula. So I'm going to delete my formula from L here. In this case, okay, for question 4 here, all right, what is L? L is 7.239 E26, and T is 7,500. And now I have to program this to calculate R for me. All right, so start with equals. Equals, I probably don't need parentheses here, right? Grab whatever value there is for L, which I put in B1, in cell B1. Raise that to the 1/2 power. Nope, not going to do that, right? That would be a mistake. Why? Because your spreadsheet knows the correct order of operations. Okay? And if I did B1 raised to the power of 1 divided by 2, right? In the order of operations, you do exponents before you divide. So if I put this in, my spreadsheet would take whatever number is in B1, raise it to the first power, and then divide that by 2, which is not the same as taking something to the 1/2 power. So if I wanted to take this to the 1/2 power, I could either do that. I would wrap this in, wrap the 1/2 in parentheses so that it would take 1/2 as the power of L, which would be fine. That would give me what? That would give me 2.69 times 10 to the 13. Or there's an easier way to do this, right? What is 1/2? 1/2 is 0.5. So just take L, raise it to the 0.5 power, 0.5, 1/2, same thing. It gives you the exact same answer. So when you're doing this kind of thing, when you're raising something to a fractional exponent, just use the decimal. It'll save you from making a simple mistake. Okay, so, all right, I got L. I'm raising it to the 1/2 power. And then I'm dividing by, now, got parentheses, T over 5,800, right? Going to take the temperature. I gave that away. Spoiler. We'll see this again in a few days, but yes, spoiler, T stands for temperature. My mistake. Okay, so T divided by 5,800, and then I'm going to raise that to the second power. All right, that should be everything. And then the spreadsheet says 1.609 times 10 to the 13th. But what's the right number of significant digits? Well, L has 4. T only has 2. So T is the one with less significant digits. So that's what I got to round to. I got to round my value of R to 2 significant digits. So I'm going to take, what are the 2 significant digits? The 1.6. So I'm going to take my value of R. My value of R is 1.6 times 10 to the 13th power. Okay. Last one. Okay. Convert from parsecs into light years if 1 parsec equals 3.26 light years, right? When you're converting units, you take the number that you want to convert, 2.86 parsecs, you multiply by the number of units per unit of thing you're wanting to convert, right? And so when you multiply by the number of light years per parsec, you're taking parsecs divided by parsecs. Parsecs divided by parsecs means they cancel out, and you're just left with light years is the only unit that survives, so that must be what your answer is going to be in terms of. And once you've canceled out the units you want to get rid of, it's just 2.86 times 3.26. I'll delete all this to clean it up. Equals, what did I say? 2.86 times 3.26. 9.324 E plus 0. See, the cell is still formatted to give me my answer in scientific notation even if I don't need it. So how can I get rid of that? Well, I could just right click on here, say format cells, and I'm going to say don't give it to me in don't give it to me in scientific notation, just give it to me as a number. And it'd say, okay, I'll give it to you as a number, in a standard notation, and that means, okay, your answer is 9.324. Except no, it's not, because this has 3 significant digits, this has 3 significant digits. I got to round my answer here to 3 significant digits, so my answer is just 9.32. There you go. Right. You got the right number. You did the math. You rounded to the honest level of accuracy. That's what a good scientist does, right? Solve a problem, give me the answer, and give it to me, with an honest amount of accuracy. Tell me how good you calculated your answer. Okay. If you got the same answers that I did, then you're in a great position. You know what's going on, and you're ready to take the tool number 1 practice assignment. If you didn't understand how I got the answers that I got, then post a question to the discussion board or come into office hours and ask me some questions, because I want you to understand what's going on so that you get all the questions right on the practice the first time. All right. So go ahead and, if everything's good, then go ahead and do the practice assignment. Okay? All right. Have a good one, everybody.